at three face to face, and that means I can definitely drop the lowest. I might
Yep.
also consider doing something once I get everybody that has taken the face to face test. I might do something where there's going to be like some assignments you can do to increase your score, and it'll be a progressive system. Like if someone made between 90 and 100, they can only add 2 points to their score. But if they made between 80 and a 90, maybe they can add four, or between 70 and 80, maybe they can add eight, or and then if
Okay.
you're like below 50, maybe you could add 15 or something.
Okay.
I'll might do something like that because that's always good just for the student to look back at the test and try to figure out
Yeah.
what they missed and how to do it correctly in case a similar question comes up later.
Is that I guess I can look right now. I don't know if I can see my answers. Okay, I
You're
can.
supposed to
All
be
right.
able to with, oh, you did see it? Okay.
Yeah, I just pulled up my face-to-face exam. I just want to see I would like to go back through and see what I did wrong.
So it did, and you
Um
just went through the grade book and clicked on the grade in the grade book?
I went through on modules and clicked on the face-to-face exam from there, and
Oh,
then it
okay.
opened up the exam
Yes,
that
I've
I took.
opened it as well
So
without the responders.
you were able to do it without the respondents too, Jennifer?
Yes.
Cool. Yeah, I think that's because I didn't really have to put the respondents on there because it was my understanding that everybody would be
Proctored.
going to a proctoring system. So
Yeah.
yeah, that makes it easier for you to do. Whereas my face-to-face class, they had to do it with a lockdown browser. So now, as far as I know, they can only see it by opening the lockdown browser, going into the grade book, or possibly going to the test itself. I don't know about that, but
Yeah.
clicking on the grade in the grade book will allow them to see what they missed. And I
Yeah.
hope it does it
And
the whole
241,
semester.
I think that's how it was.
Yeah.
Yeah.
Yeah, when I took it with you face to face.
That's cool. All right.
Um,
Well, I did do, and people haven't been here too terribly much lately. I know you two consistently come here at least a little bit late or leave a little bit early or something. But how are y'all feeling about the Gauss's law applications?
let me go to the book. I mean, honestly, my plan was, I mean, I had a conference yesterday, and this week I was preoccupied with other stuff. Unfortunately, I didn't have enough time to look at it. But
Gotcha.
from
Well,
lab, we did go over Gauss's law briefly.
hmm
Um, and so I do remember kind of like the basic principles.
Okay.
What
Well,
chapter? We're in chapter
that's
22?
22 was the Gauss's law,
Yeah.
and I've done plenty of examples, so I'm really leaning towards jumping into chapter 23 right now.
Yeah, I
Go
just
Um,
for it
finished
though.
22's homework, so I think
you're going good on that, Jennifer?
I think, yeah, sure.
Yeah.
We'll call that
Sure.
a yes.
Don't ask me about whether I'm doing good. Darn it. I did my homework. That's all you need
I
to know.
am here and I'm doing stuff, so I am learning
Okay.
things.
Gotcha. Well, the main thing I wanted to point out is I did put a bunch more videos on our 242 course. What I noticed is it looked like most people were just going straight to my YouTube channel, so I wasn't even updating like the latest lectures because I figured y'all were just going that way.
Nuts.
But that was another complaint that I got was that my modules weren't made up, and that's a perfectly reasonable complaint because I just figured, what, it's a lot of work for me to do it. Why was I doing it if the people automatically know to go to the YouTube channel? But anyways, I went ahead and set that back up and caught it up to date. So there's a bunch of videos on there now. The big thing to remember, and this is key, there's two major points with Gauss's law, the way we're using it. What we use is Gauss's law, which is the closed integral of E dot dA
Mhm,
is equal to Q enclosed over epsilon naught.
mhm.
And the big part of this chapter 22 is about using that vector, or excuse me, that integral equation to extract the magnitude of the electric field out of the integral equation. And it is Gauss's law, so it's always true, but you can't always do that little trick that we're doing in chapter 22. The only way you can do that trick, which again is finding out the magnitude of the electric field and extracting it from that integral equation, you can only do that when you have one of three symmetries. It either has to be a spherical symmetric charge distribution, again, spherically symmetric charge distribution, or a infinitely long cylindrical distribution. So, like the very long wire we did in the very beginning of chapter 21 when we first started covering integrals of Gauss's law, or of Coulomb's law, excuse me, or for an infinite plane. And the key to that is when you want to use one of those three symmetries, the left-hand side is always supposed to be the easiest part, and the answer always comes out to be the magnitude of the electric field times an area, maybe times a number, and it might be, some terms where plus zero is added or something, but the main thing is it's always going to end with the left-hand side being the magnitude of the electric field times an area and maybe times a number. The right hand side is where the hard part is. And the final thing I wanted to remind you is because those are the only types of symmetries, we can use Gauss's law for solving for that particular electric field magnitude. It turns out there's only really three Gaussian surfaces that you need. And for the spherical Gaussian surface, you need a concentric sphere for the Gaussian surface. For the infinitely long cylinder, in other words, the infinitely long wire, you need a Gaussian surface that is a cylinder, and it's not infinitely long. The cylinder will have a very distinct length L or height H or whatever you want to be, but it will be a cylinder with a top and a bottom. And when you're doing the infinitely long wire, the part that doesn't go to zero is the electric field around the soup label, but the top and the bottom give you zero. And then finally, if you're doing an infinite plane, you again use a cylinder, but this time the top and bottom of the cylinder is the part that gives you the electric field times the area, and the soup label gives you zero. Okay, so just keep that in mind, and I have this on video now. Of course, that was the main reason I wanted to make sure I said it to you, is so I give it to you, but also because it'll be on video. So that's a key thing. The left-hand side's always a number times E times A, or just E times A. It can have plus zero terms, that sort of thing, but that's what the left-hand side is, and you only have three Gaussian shapes that you're going to use: a sphere for the sphere, a cylinder for the infinitely long cylinder, and a cylinder for the infinite plane. So hopefully that'll help it settle in your brain a little bit more if you're not so worried about all the different possible problems, because when you look at it that way, it starts to feel like, you mean there's really only three problems we can solve? And in some sense, you're right. There's really only three problems you can solve this way. Okay. So hopefully that makes it a little easier. Anybody have any questions on that before I jump on into chapter 23? Okay.
Yeah.
Uh, do check that out. Make sure you read the section about, where it has cavities inside of a conductor. Make sure you understand what I talked to you about with regards to conductors. We learned in chapter 21, for instance, that when you put loose charge on a conductor, it turns out all the charge is free to move. That's the nature of a conductor. And therefore, all the charge will move out to the outside surface of the conductor and distribute itself over it fairly uniformly to minimize the potential energy. Because of that, you get all the charge completely being on the outside edge of the surface of any conductor. Now that we know Gauss's law, you can go back and look at any conductor knowing that that's the case about where all the charges will reside, and you can take a Gaussian surface just inside of the surface of the conductor, make it the exact same shape as the conductor, and because of that, if there's no cavities with extra charges inside and stuff like that, because of that, you'll get the charge enclosed as zero. So the right hand side of Gauss's law is zero. And the only way the right hand side of Gauss's law is zero is if the electric field is zero everywhere on that Gaussian surface. The Gaussian surface being literally a replica of the actual charged surface of a conductor that you had. So what we've now learned by using Gauss's law in conjunction with what we learned in chapter 21 is that in electrostatics, not only does all the charge go to the outside surface of the conductor, but the electric fields inside the conductor is zero. Now, electrostatics is not a case where you connect a battery to a wire, for instance. Once you connect a battery to a wire, then it's no longer electrostatics. It actually can compel the charges to move continuously away from the positive charges, is the way we picture it, and into the negative terminal of the battery. So hopefully that helps you. But like I said, you can get that from the reading, but you can also get it from all the examples I worked and stuff. But feel free to ask me if you have any problems. So, what we're doing now is chapter 23, and chapter 23 is called just electric potential. And they use that word very intentionally, the word potential. It makes you think of potential energy. And that is one of the things we're going to, excuse me, that is one of the things we're going to study is we're going to study the electric potential energy. But we're also going to introduce a new quantity that's called the electric potential. Notice I stopped short of saying energy. When you say the electric potential, we mean electric voltage in that case. But when we say electric potential energy, we mean potential energy, which is measured in joules. Okay, so keep that in mind throughout the whole course because that's a big deal. So this voltage turns out to be potential energy per unit charge. So the actual unit of a volt, 1 volt, is 1 joule per coulomb. That's where we'll get it from. So what I want to do now is go ahead and take a couple sentences that I wrote out to help you better understand exactly what we're doing. I'm going to go ahead and share my iPad screen, partly because if I don't remember to do now, I will forget it and then forget to do it later like I did last night. But it should pop up there in a second. And it's my handwriting, so I apologize. It's not as good as it should be. But I do have a keyboard that my wife bought me for this iPad somewhere, and I can't find it since we moved everything. So it's a pain having to write everything. But here it is. It says potential energy functions can only exist if a conservative force exists. You might remember that from when we talked about conservative forces. I think it was in chapter 7 or it might have been chapter 8. I can't remember. But the main thing is once you have the curl of a force is identically zero, then that proves that the force is conservative. And a long string of facts comes out if any one of those facts is true. One of the facts is del cross F is equal to zero, and that's the one of the definitions of a conservative force. Another one is if the path integral or line integral from A to B is in general independent of path, and therefore only depends on the endpoints, then that also is indicative of a potential energy function and due to a conservative force. Or if you take the work done in a circle, in other words, where you start at one point and end up back at the same point, that work will be identically zero. That's another indicator that you have a conservative force. So we call forces conservative when they have a curl that is identically zero, and such forces lead us to develop conservation of energy laws. Uh, so it turns out that the change in potential energy, delta U, is defined to be the negative of the work done by a conservative force. So that's sort of like the underlying definition. Like if you discovered a new force that you'd never seen before, you might want to say, well, it'd be really good if I could get this out of the vector world and into the scalar world. So I'd like to make up a potential energy function. The way you'd go about doing that is calculate the work done in moving a particle from A to B, for instance, and then set that work equal to, or that negative of that work equal to the change in potential energy, and then maybe you can get a potential energy function. That's what we did with calculating the work done in lifting an object from ground height to some height h, and we end up getting a potential energy function m times g times h. We did it again with Newton's law of gravity. F equals G m1 m2 over r squared. And in that case, we ended up getting negative Gm over r, or negative Gmm over r. So this is what we do. We say work is equal to the integral of f dot dl, but we got to remind ourselves that we're only doing this specifically with a conservative force. And it turns out, since Coulomb force looks just like yeah. Since the Coulomb force looks exactly like the Newton's law of gravity, you remember it's Newton's law of gravity is F equals G m1 m2 over r squared. Coulomb's law is F equals K q1 q2 over r squared. So they're identical, right? Because of that, we know that we don't have to even do the testing. We can just say automatically the Coulomb force is a conservative force. And since it's conservative, we can take the integral of that force in going from, let's say, A to B, as I've written here, work equals the integral of F dot dl, where F is a Coulomb force. Then we set delta U, the change in potential energy, which would be U final minus U initial, which I called UB minus UA. We set that to the negative of the integral from A to B of the conservative force which I'll call F sub C, just to remind us it is a conservative force like this. Okay? So with that in mind, you can start to see what's going to happen. And in fact, what we're going to do is we're going to define delta V, the change in voltage, is going to be equal to delta U divided by Q. Now, if you look at the line above and apply this, what you'll see happens is we'll get UB minus UA over charge Q is equal to, now we had the negative integral from A to B of the conservative force dotted with dl, but we're actually dividing that by Q. And it turns out we can do that and we just get the negative integral of E Coulomb dot dl, because as we learned, E was, remember, the limit as little q approached 0 of F divided by little q. So what we've done by dividing through by Q is we've converted the integral, which was a negative integral of F dot dl, to a negative integral of E dot dl, and therefore we will say the potential energy function U is equal to basically whatever we get, or I'll say it like this: delta U is the negative integral from A to B of E dot dl. And this is sort of our fundamental formula that we're going to use over and over again. In fact, we're going to use that to figure out, for instance, what the change in voltage and change in, ooh, excuse me, this is supposed to be, I wrote delta U, but I meant delta V. Uh, Glad I caught myself on that one. I'll take a couple steps, that way it'll make a little bit more sense. What I'm going to say is this quantity, of course, is delta V, which equals delta U over Q. So you could say delta V, which equals VB minus VA, is the negative integral from A to B of E dot dl, and that's really the sort of fundamental idea that we need. So this is what we're going to use, like I said, later when we consider a capacitor and we want to calculate the voltage between the two plates. This is how we'll do it. The change in voltage is equal to the negative integral of E dot dl. Now that we have that settled, I think you have some understanding of exactly what voltage is, and I want to tell you that 1 volt is defined to be 1 joule per coulomb. So that's another important result, and you can see exactly where it came from. As you can see, delta V is delta U over Q, so that's why it's set up that way. Now that we have that, I wanted to point out something that your book points out for good reason, and that is, let's imagine we have a really large positively charged plane. So this charged plane right here is positive, and we're looking at the edge. We're looking at an edge on. It runs into the page, and then some distance away, hopefully a small distance compared to the distance to the edge, we'll put another plate. But in this case, the plate is going to be negatively charged, so I wrote it negative with a red line beside it. Okay, so this side right here on the left is the positive plate, and we can pretty much just imagine it as having a string of charges like this, and then we can imagine this side having an equal number of charges on the other side, because that is ultimately what we will treat as a capacitor. So this is a capacitor, but we haven't learned it yet. What we do know is the electric field. This is a big important sentence in case you haven't picked it up yet from the reading or from the multiple times I've said it. Big important sentence coming. The direction of the electric field is the direction in which a positive charge would be compelled to move if placed in that spot. So we can tell, for instance, if we took a positive charge and put it up against that left plate, we know for a fact that the electric field would run from the positive charge to the negative. And really, if you go back to the 1800s when this stuff was being developed, they saw the field lines as if they're real things. And they pictured the field lines only existing as coming out of positive charges, and then they only cease to exist when they run into a negative charge. So it's not that I'm just showing you an arrow going from left to right. It's that I'm showing you an arrow that's been created by the positive charge on the left, and then the arrow dies out once it gets to the negative charge on the right. Okay. And in fact, as you get near the edges, what's going to happen is the electric field might curve out a little bit, but y'all did that in your electric field mapping lab as well. So the big deal is, as long as you stay towards the middle of the capacitor, you won't have to deal with those fringing effects, and you get a nice uniform electric field. So now what we're going to do is we're going to imagine putting a charge next to the positive side, and that's going to be a positive charge. And what we see is going to happen is, because of the existing electric field, the positive charge is going to move from this point A to this point B. And we know that it would do it all on its own. Okay. So we can take our idea that the change in potential energy is equal to the negative of the work done. And from that, we can say that delta U, which is really going to be UB because that's the final position, minus UA because A is the initial position, is going to equal the negative of the work done. And it turns out the work in this case is an integral, but the force is actually a constant because the electric field's a constant. And not only that, we're going directly along the field lines, so they're parallel. So the integral of F dot dl just becomes F times L. But we know F in terms of the electric field is, so let's label this charge here. So this charge is a positive Q. So I'm going to now say that the negative of the work is the negative, and then if we take the Q and multiply it by the electric field that exists in the between the plates, so I'll call that E right here, then negative Q times E is the force. And if we say, for instance, that this distance from here to here is D, then we get QED is the actual work done times, of course, now we got to multiply that by a negative because we wanted the potential energy from that. From this, what we see is that the positive charge will actually, on its own, be compelled to move away from a positive plate and to a negative plate. And it's going to do it on its own. So that means since the positive Q will move from A to B spontaneously. Don't you hate now that you've had that word in thermodynamics, now we're using it all over the place. So it's going to move spontaneously from A to B. We know, oops, since the positive Q will move from A to B spontaneously, we know that delta U is less than zero because it became more comfortable. Okay. Remember, we sort of talk in terms of comfort, like a positive charge does not want to be near another positive charge, so it's a little uncomfortable. You can also make an analog to that in terms of humans. In general, humans do not like super high heights, right? You would not enjoy. I don't know. I see these people doing it on like TikTok and stuff all the time, where they'll like get on top of a rock ledge and it's like 1,000 foot drop, and they'll jump up in the air and just for the heck of it, like talking to their dog or something. And I'm like, ugh. But yeah, so just like you imagine, you would not feel comfortable really, really high up over a 1,000 foot drop. You're not going to feel comfortable as a positive charge being next to a positive charge, but you will feel comfortable next to a negative charge. So the fact that the positive charge moved from the positive plate to the negative plate spontaneously tells us it went from discomfort to comfort, and therefore the change in potential energy was a decrease. So it actually lessened the potential energy. All things, in fact, tend to go to a decrease in potential energy on their own. So I'll write that as well. All things spontaneously tend to move from discomfort, which means U is big, to comfort, which means U U final is much, much less than U initial. So it might not be necessarily correct to always say UI is much, much greater than zero. There are principles, and you could always put the zero in such a way where that's not necessarily true. But this last part is definitely true, where U final is much, much, much less than U initial. Say, so I'll put here and I'll just say possible, but
So
not
it's always
required.
decreasing.
Exactly.
Yeah. So the
So yeah,
value of yeah.
yep,
So
that's it.
the and like the negative QED, remind me, D is distance, or is that
Yeah,
our
d is the distance between,
okay.
and that's only because in this case the electric field was a constant. Otherwise, you'd have to do the integral stuff and all that,
Okay.
right? So, in other words, the QE is just F, and then the d is just the distance. So, instead of doing an integral of F dot dl, all we had to do was multiply F times L, but the L was
Right.
g and the F was QE. Does that make sense?
Okay. Yeah.
Okay. So all things spontaneously tend to move from discomfort, which normally just means a high potential energy, to comfort, which means the final potential energy is less than the initial potential energy. So now that we got that, we have some sense of what that means. And you could also, for instance, consider putting a negative charge there, and you would reach a different set of conclusions, but I want to make sure you understand the conclusions from this diagram. So, since we're going to say delta V is delta U over Q, and we found that delta V, or we found that delta U was negative Q E D, then delta V is going to be negative QED over Q, and that's going to be negative E times D. Okay? So, what we can see here is for the charge positive Q, one, it naturally moves from. Now, you might not be able to see it with the equation that I have written in purple immediately above, but I'm going to go ahead and write this as VB minus VA, since that's the change in voltage, right? So you see it naturally moves from, since we just discovered that delta V is negative, the VB must be lower than the VA. So it moves from high voltage to low voltage. So that's a big thing that we wanted to figure out. But remember, that's specifically because we did it with a positive charge. For instance, because the formula has the QED in there, the potential energy has the Q, you would put in a negative charge and you'd say that the potential energy might do something a little funny. But now we're also going to look and realize that it naturally moves from uh, from high potential energy. Whoops, I made it energy to low potential energy. As all things do. Okay. So the positive charge definitely moves from high potential energy to low potential energy because everything does that. But we've also been able to put together that clearly it went from high voltage to low voltage. Now, if we set up the same setup, but for a negative charge, let's say I use this little gray charge here. If I put a negative charge here, it would, in fact, on its own, be compelled to move the other way. And basically, we know that because F is equal to Q times E. So the force that a charge Q would feel in an electric field is Q times E. Well, the E is pointing to the right and the Q is negative. So when I multiply a negative times a vector going to the right, then you get a vector going to the left. So in that case, for a negative charge, negative Q, the for negative Q, actually, I'll put it a different way. I'm going to say 1, it moves naturally. There I go again, using an M when I mean an N. It moves naturally from high U to low U. But the other part here is too, it moves from low V to high. So that's different. Both the positive charge and the negative charge always go on their own in the direction of decreasing potential energy, but that forces the negative charge to move from the low voltage to the high voltage. So when we look at a battery and we think, okay, here's a positive end of the battery, here's a negative end of the battery, and we connect a wire briefly, mind you, because you need more than a wire if you're going to connect the positive end to the negative end. But if you just briefly connect the negative end and the positive end together through a wire, what we picture is little positive charges running from the positive end of the battery to the negative end of the battery. In reality, we've learned that you can't really break the positive charges out of the lattice that makes up the wire. It's more likely that what's going on, or it's actually is what's going on, is that individual electrons have broken free from the atoms that are stuck in the lattice, and the negative electrons are what's loose, and they are actually running from the negative terminal of the battery through the wire to the positive terminal.
Like,
Uh,
isn't it just passing electrons essentially?
exactly. And that's the same thing with
Yes.
heat conduction too. So it
Okay.
turns out it's the electrons carrying all that, and they're going the opposite way. But it turns out that even though we are going to continue to use what we call conventional current, which is pretending positive charges are leaving the high voltage and entering the low voltage, it turns out there's only one experiment you can do that would discern which one's right and which one's wrong. So you're never going to make a mistake by assuming the opposite unless you're doing the same thing, which is called the Hall effect. And the Hall effect basically is if you imagine subjecting a wire carrying a current, if you imagine subjecting it to a another field like a magnetic field or electric field, what you'll do is you'll get a pileup of electrons on one side or a pileup of positive particles on the same side, and then you can measure the voltage difference between the top of the wire and the bottom of the wire. And when you measure that, it becomes patently obvious that it really is the piling up of negative electrons or negative charges on one side that is happening, and therefore you know it's really the negative charges that are moving. But they do talk about that in here. Okay. So all of this stuff was really about you trying to make sense of potential energy versus electric potential. So again, voltage is also called voltage is called electric potential, and the units of V are the volt, which is defined to be 1 joule per coulomb. And then there is electric potential energy, and that is U, which has units of joules. Okay, so it's totally different, and you've got to keep those straight, but you now have some sense of what happens. So, for instance, we know that a positive charge will move this way from high voltage to low voltage, but it's also moving from high potential energy to low potential energy. Then we could also say a negative charge is going to move this way, and it's moving from low voltage to high voltage, but it is also moving from high potential energy to low potential energy. Okay, so those two pictures pretty much sum it up, and hopefully that's good enough to give you some idea of what we're talking about here. So we can say in general that V, for instance, at A is the potential energy at A divided by the charge Q. That's at the point A. So this is another fundamental equation we can think of in addition to the one that I gave you down here, which was delta V equals the negative integral of E dot dl. So now that we have that, we can go about doing some individual problems. So for instance, you say, suppose a negative charge uh, let's say E minus, which has a charge Q equal negative 1.602 times 10 to the negative 19th coulombs. Suppose a negative charge Oh, this is not the one I want to do. Suppose a negative charge is accelerated through a potential difference of 5,000 volts. Notice I am saying that that has 3 sig figs. That's the key, or 4 sig figs. That's the key thing I'm trying to put in there. So suppose a negative charge, like an electron, is accelerated through a potential difference of 5,000 volts. One, which direction will it naturally move? And I'll call that A instead of 1. And B, how fast will it be going at the end? So that's what we're trying to solve here. What we know is delta U is equal to, uh, as we sit up here, we could say delta U is equal to Q times delta V. So that works fine. What we want though is we want delta U to decrease because that's the way that an electron would naturally go. So delta U should be less than 0. And in order for that to happen, that means delta U times negative 1.602. Actually, I should probably write that a little better. Negative delta U is negative 1.602 times 10 to the negative 19th coulombs times the electric field, or excuse me, times the change in voltage. Because we see that's what's going on, if delta U is less than 0, then delta V has got to be greater than 0. So for part A, the electron could go or could travel from V equals 0 volts to, or excuse me, from V equals, yeah, from V equals 0.0 volts to V final, I'll say that VA, equals 5,000.0 volts. So that's the direction it's going. It's going from low voltage to high voltage. And then part B, all we have to do is say that delta U is equal in magnitude to delta K. And I say in magnitude because basically I'm picturing the delta, the change in potential energy being completely converted to change in potential energy, and I'm not worrying about signs. You could, use your normal delta K plus delta U equals 0, or you could use my way where U initial plus K initial is equal to U final plus K final. But this is just a quick and dirty way of doing it. So we can say, since delta U is supposed to be Q times delta V, we're just going to take the magnitudes of the numbers without any signs. So we got Q, which is 1.602 times 10 to the negative 19th coulombs. That times the change in voltage. Again, I'm trying to work with positives, so I'm just going to write 5,000 volts right here, and that's equal to 1/2 the mass of the electron, which is 9.109 times 10 to the negative 31 kilograms. That's something you would be given, by the way, and times v squared. So we just set delta U, which is Q delta V, without paying any attention to signs. We just set the magnitude of that quantity equal to the magnitude of 1/2 mv squared, and we get V is equal to what I'm going to do is take 1.602, oops, 1.602 times 10 to the negative 19 times 5,000 volts. Now that gives me a unit called the Coulomb volt, and it's 8.01 times 10 to the negative 16th Coulomb volts. Now I'm going to multiply it by 2 to get rid of the 1/2 on the right, and then I'm going to divide it by 9.109. Divide it by 9.109 times 10 to the negative 31st. And that's going to give me 1.75 times 10 to the 15 is equal to V squared. So 1.75. I used 4 sig figs on everything. So the 7, 5, and the 7, the 5, and the 8 should all be sig figs, but then there's a 7, 0. So I'll say 7, 0 are not significant figures, and that's times 10 to the 15th. And that comes out to be meters squared per second squared, so that the velocity is the square root of that. So I'm going to raise it to the 0.5 power, and that gives me 4.194 times 10 to the 7th meters per second, which is creeping kind of close to that speed of light. It's literally more than 10% of the speed of light. So technically, we probably shouldn't be using 1/2 mv squared, but that's okay. It gave us an idea of what we're looking for. Any questions on that one?
No,
Okay.
I
So
do have
this
to go though, so
Okay. Well,
thank you.
thank you for coming, Jen. I'll finish up the rest, and it'll be posted tonight or first thing tomorrow morning at the latest. This is just
Okay,
like
great.
example 23-2. That's more or less the same type of example as we did there. So that should help you a little bit in discerning what I'm doing versus what the book's doing. We haven't gotten very far in chapter 23, but now I want to show you how we can do other things with it. So we did already learn, for instance, that VB minus VA, which is delta V, which is also VBA, that's another way your book is using it, okay? That's equal to the negative integral from A to B of E dot dl. So that's again that same equation I boxed off before, but that's pretty critical. That's how we go about calculating voltages. And we got to remember it is a quote unquote line integral. And as I told you last semester, when you do a line integral, you have to either decide whether you're going to use the limits of integration to dictate which direction you're going, and then the DL will just point in the positive coordinate direction, or you can let the DL explain which way you're going, and then you just put the A and the B in increasing coordinate direction. One of those two have to be done, but if you end up doing both of them, you can actually be off by a negative, which is a bit of a problem. So with that in mind, we can, for instance, find out what the voltage difference is between two plates of a parallel plate capacitor. So we worked out before using Gauss's law that, and I'm going to try to change colors to something other than this. From Gauss's law and previously from Coulomb's law, we found the electric field strength near an infinitely large, uniformly charged, charged plane is E equals sigma over 2 epsilon naught, and it's perpendicular to the plane. Okay, we found that out. We did it just the other day also with Gauss's law. We did it before with the circular disk, and then we examined when the distance z away from the circular disk was small compared to the radius r, we got exactly this expression sigma over 2 epsilon naught. So if you try to break down parallel plate capacitor, I'm going to draw them edgewise like we did just a second ago, and I'm going to imagine them really, really close to each other. So we'll put it like this, and in fact, this one is going to be the negative charge, and this one is going to be the positive charge. And what we really found was that if you had a plane, let's say like this, and you set it such that this was your y-axis, this was your x-axis, and this is your z-axis, then what you found was E was equal to positive sigma over 2 epsilon naught k hat for z greater than 0, and it was negative sigma over 2 epsilon naught k hat for z less than 0. So if we just attack that for a second, looking at this positive plate we have, I want to ask you at this particular location, Josh, do you know which direction the electric field due to that positive plate will point? I'll give you a hint. It's either left or right, up or
Well, it's
down.
going to be to the right.
To the right? Okay. So what I'm going to do is take a red pen, because that's the one we're talking about, and point it to the right, and we know that value is sigma over 2 epsilon naught. What about over here? Again, just thinking of the positive plate, what direction will the electric field point over here?
Uh, I mean, would it continue to point to the right, assuming
Uh,
that's the direction?
check
What do you
out
mean?
check out this expression.
Are we going to the left? One.
Yeah, see this down here? This applies to this plane. So up here, the electric field points up. That's why we have the positive. Which direction does it point down here, though?
Negative.
Okay, so which direction does the electric field point over here? Just do, again, ignore the negative plate, just thinking about the positive plate.
Uh, Positive plate. So it's going to the positive to the right, so it's negative to the left.
Exactly. Yep, so that one's sigma over 2 epsilon naught as well. Now, let's do the same thing for the purple plate. And the purple plate, of course, is a negative charge. So basically, you're going to replace the sigma that we have in this little expression that I wrote. You can imagine that being a negative sigma. And then, of course, the signs will flip. So between the two plates, what is the direction of the electric field due to the negative plate? Completely forget about the red one. Only think about the purple one. Which way will the electric field point in here?
Um, well, does the negative have anything to do with it, meaning that the poles would be reversed?
Yeah. In other words, the plate looks negative to any charges that are around it, whether they're on the left side or the right side of the plate. It's always going to look negative. So, which way would the electric field point on the left side of that purple plate?
To the left? On the left side?
It's actually to the right because remember, it's now negative, so it's attractive to positive charges. So that's going to
Okay.
give you sigma over 2 epsilon naught as well.
Okay.
Does that make sense? Because the plate is literally just a bunch of negative charges, and the electric field direction is defined to be the direction a positive charge would be compelled to go. So if I,
Oh, okay. Yeah, yeah, yeah.
okay, what
So then
about
on the
now?
right side,
Yeah,
On the right side, it would be to the left.
exactly. So now I can
Yeah.
take and put the this way. And of course, we already know that since the purple was pointing to the left, but to the left of the plate, we also know it's going to point to the right, or excuse me, to the right, to the left of the plate. So this is going to be a sigma over 2 epsilon naught
So
here as well. And this one's going to be a sigma over 2 epsilon naught here as well. But we also know that the electric field due to the red plate is going to point to the right over here as well. So what you see is you've got equal magnitudes but opposite directions on the right-hand side. So E is equal to 0 over here. And you got the same thing over here. So E is equal to 0 here. But in between, you end up getting sigma over epsilon naught because they're both pointing to the right. And when you add them together, you get sigma over epsilon naught because it's sigma over 2 epsilon naught plus sigma over 2
yeah,
epsilon naught. That make sense?
yeah.
So
Okay.
now what I can do is I can create my own coordinate system. I'm going to say this is my x direction, this is my y direction, and I'm going to say that this point right here is point A, and this point right here is point B, and I'm going to go about calculating delta V, excuse me, delta V, which is VB minus
VB
VA,
minus VA.
which
Yeah.
is a negative integral E dot dl. Okay, so I'm going to calculate that. The E is going to be just a constant, sigma over epsilon naught, but it's going to point to the right, which is the I hat direction. Now, the dl, this is where we have to decide, since we're doing a line integral, we have to be very careful and make sure we choose our directions properly. I'm going to choose that the dl indicates direction of integration. Let dl indicate direction of integration. So that means since we went from low x to small to high x, that means dl is going to equal positive dx I hat. Okay? And A to B should be from small x to large x. Because once we've decided that the dl tells us the true direction, then we automatically just go in the positive coordinate direction for the other part, which in this case is a limit of integration. So I can now say that delta v, which is vb minus va, is equal to the negative integral. I'm going to say from x equals 0, and I'm going to call this little coordinate here d, to x0 equals 0 to d. That goes from small x to big X, just like we wanted. The E is sigma over epsilon naught times I hat. And then the DL is positive dx I hat, which we learned that the dot product is a vector, is a linear operator, so we can actually pull the dx and the sigma epsilon naught. We could pull them right in between the dots, or we could pull them out. I'm going to pull them out, and the fact that sigma over epsilon naught is a constant, I'm going to write it out in front. Say sigma over epsilon naught. Now I have the integral from 0 to d of dx, and then we have the I hat dot I hat, but that's just 1 times 1 times the cosine of 0 degrees, which is 1. And of course, the derivative, or excuse me, the integral of dx from 0 to d is in fact just d. So I get negative sigma over epsilon naught times d. And that's the change in voltage. And we should expect that change in voltage to be negative, and that's exactly what we got. We went from the high voltage positive side, which obviously, if you were connecting to a power supply like we've used in lab, which might look, for instance, like this, and we're actually using the positive side and the negative side. Oop, that was supposed to be black. Sorry about that. Okay. And of course, we're using the DC side as well. So what we would do is we'd take the red cord or the red terminal and connect it to the positive plate, and we'd take the black cord connecting it to the black terminal and connect it to the negative plate like that. And that would be exactly the way we try to make one plate positive, one plate negative, as we did in the electric field mapping. So does that make sense?
Yeah.
Okay.
Um, I got a split here to go
Okay.
to lab.
No
So
problem. Thanks. I'm
thank
gonna
you.
maybe finish up one more example. I don't even know that I'm gonna do that, but you have a good one, Josh.
All
Take
right.
care
Thank
and
you.
holler if anything.
Yep.
All right.
Yep.
Thanks.
Will
Bye
do.
bye. Okay. So now my other person left. I should probably regroup and just say that the voltage across a capacitor, V capacitor, is equal to the electric field in the capacitor, which is a constant, times D. And I should say that the electric field in the capacitor, as we just worked out, was sigma over epsilon naught, and it pointed in this case, it was the I hat direction, but more generally, it points from positive plate. I think Allie wants to come in, baby, to the negative plate. Okay, so that really is the expression that we got for it. And in fact, we can now answer a question, uh, which is this. So let's look at this is going to be example 23.3. And actually, we got a couple minutes for class is supposed to be over anyway. It's supposed to run until 6:40. So I'm going to definitely keep on now. So in this example, where I said we're saying two parallel plates form a capacitor with a potential difference, oops, of 50.0 volts if the separation D is 0.0500 meters, then what is the electric field between the plates? So what we're going to do here is solution. And what we just discovered was the voltage across the capacitor is equal to the electric field of the capacitor times the separation of the capacitor. And we found that the electric field, of course, is a constant between the plates because we put the plates so close together that they do behave like they're infinitely large. And as long as we stay away from the very top edges or the front edge or the back edge or the very bottom edge where the electric field can sort of bulge out as I drew earlier in this one, where you can see it bulging out here and here. Because of that, we can just set all of this equal to, I'm going to say 50.0 volts is equal to E cap times 0.0500 meters, and that gives me that the capacitance electric field, in other words, electric field between the plates of the capacitor, is equal to 50.0 volts divided by 0.0500 meters. And lo and behold, not only are we going to get a really neat number that you'll be surprised at how big it is, 50 divided by zero point zero 0.05 gives us 1,000, but we're also going to get a new unit, which is volts per meter. And now all of a sudden we have a much more useful unit to think about the electric field strength. So the answer is, in fact, 1,000 volts per meter. There should have 3 sig figs. Okay, so I have to actually underline this other zero as well. So we really should call it 1.00 times 10 to the third volts per meter. But we did learn that the electric field strength, which we learned was 1 Newton per Coulomb, is evidently also equal to 1 volt per meter. So we can use that now as well. Hopefully that's pretty helpful going forward. I don't think we have really much more time, so I guess I'll call it here, and I might do some more videos later just to get you guys up to speed for chapter 23. I would like to go ahead and try to finish chapter 23 this week, so I'm going to make some more videos, enough for us to kill chapter 23 for the week. You guys have another video or another class on Thursday, but I think I should be able to do all of chapter 23 on construction videos that I might construct between now and then. So I'm going to go ahead and call it a day. Uh, so let's stop the sharing. Thanks for coming, everyone, and feel free to contact me if you have any problems. Don't forget to get your tests done, that sort of stuff. By the way, I did open another online test, which I called test 4 because it's the fourth test, but it's the third online test. And I've decided to give y'all till the 16th instead of to the 9th, which is what it was originally slated for. I did change the syllabus, but I'm not going to do that in the future. It's a pain in the butt. So I'm just going to let y'all know through these videos, as well as possibly I might let somebody know something through the email, but you should be watching your videos too. So have a good one, everybody. Bye bye.